In previous videos, we talked about drawing different graphs of data. We learned about histograms and ogives and all these different things here. And now we're going to try to introduce some terminology that we will use to describe the types of pictures that we're going to see. So remember, distribution at its default is just a list of the values and their frequencies or relative frequencies. But if we turn that into, histogram, then we actually have a picture here. And depending on what the picture looks like, we give these different names. So a uniform distribution, at least by definition, is going to be when all of the frequencies or relative frequencies are all equal. Now, they don't really have to be perfectly equal because, again, nothing in real life is going to be perfectly working out. So if your actual distribution looks something more like this, where, some are a little higher, some are a little lower, and so on, as long as they're all pretty much even height, that's what we call a uniform distribution. So again, uniform means everything is spread out uniformly. There's not really anything that's standing out. They're all about even here. That's what we call a uniform distribution. And, there are certain situations that this will come up naturally. For example, let's say you're going to roll a dice, and it can be any number 1 through 6. Well, if you keep rolling that dice over and over again, let's say you roll it 1,000 times or 10,000 times, and you record how many 1, 2, 3, 4, 5, and 6s there are, it's going to be roughly even. It's not likely that it'd be exactly even because there's randomness, there's things that would affect that, but that would be what we would call a uniform distribution. The second one, and this one's going to be very big, we are going to be seeing this over and over and over again in this class. It's very common. Some people call it bell-shaped. You may have heard of the bell curve before. One of its official names in math is normal, and another way of calling it is Gaussian, named after a famous mathematician, Carl Friedrich Gauss, who studied this. But no matter which one it is, what name you use, they mean the same thing. The idea is somewhere in the middle of the distribution, you're going to have really high frequency results. And then as you get further away from that middle part there, things become less and less likely. And that happens both on to the right of the high point and the left of the high point. So if you wanted to try to make it look perfect or really nice here, it's going to look something like this. And that could probably be drawn better, but that's the idea here, is that somewhere in the middle of your graph, that's where you're going to have the highest frequencies, highest relative frequencies. That's the most common scenario. And as you go bigger values or smaller values, further to the right, so that means these are values of the variable that are bigger than the common ones. These are values of the variable that are smaller than the common one. Either side, they're going to happen less likely. So in the typical bell curve you've probably heard of before, like in grades, a lot of times, this middle part here might be, say, a C, and then, most people are in the C range, and then there are fewer people in the B range, and even fewer in the A range. Similarly for D's and F's, something like that here. There are many other situations that also fall into this. If you look at height of adult men, it's going to look something like this, where you have the kind of average height in the middle, that a lot of people are near that, and then there are fewer people that are significantly taller than that, and there are a few people significantly shorter. Weight of adult men, similarly, you can also do height or weight of adult women. You don't want to join them both together and just say the height of adults, period, because there isn't really one value that all adults, men and women, that are kind of mostly around that. So what you would end up having is you end up having, for if you wanted to combine adult men and women here, you'd kind of have something where you have this high point where a lot of women are around that. Maybe it's not so deep down here. And then you have another high point where a lot of the men are around that. And so it'd be a bimodal distribution. I'm mentioning that right now because it's kind of related to what we're talking about, but I want to cross it out because It is not bell-shaped normal Gaussian when you have the two different separate humps there. Bimodal is not going to be included in this category. You should only have one main hump right in the middle of your graph in order for it to be a normal distribution or a Gaussian distribution or a bell-shaped distribution or a bell-shaped curve, any of those words there. Now you look at my specific example with my histogram here, you see in this case, you know, technically maybe it is bimodal, there are 2 points there, but it's, you know, they're all kind of right in the middle. So there's the perfect graph, and then there's the real world data that's not going to be exactly perfect. And it's always going to be down to the interpretation of whoever is presenting this to decide whether it's close enough to the true graph for a bell shape or not. We will talk a little bit about maybe some calculations you can do to try to see whether it's truly in the bell shaped or not, but that'll be for later. Then we have these two things here called skewed left and skewed right. Honestly, this is something that a lot of students switch them up. So we want to try to talk about it. Like, for example, let's say I drew the following two graphs here. There's one, and then here is the other one. A lot of people might say, well, oh, in the first graph, the high points kind of to the right side, so that'd be like a skewed right graph. And on the second graph, the high points kind of on the left, so it'd be left skewed. In fact, that's the exact reverse. So this first graph here, and let me maybe try to make it even more clearly skewed left. So this is in fact a skewed left graph. And if you want to think of it in terms of a histogram, that means you've got a good amount of data, you know, commonly data essentially on the right side here, but there are data points, lots of them, even if there are not that many people, but there are data points that go really far to the left. So the idea is you have your high point, your mode, right, your most common region of your graph, and then there are many values significantly to the left of that, more values to the left compared to on the right here. This is called the left tail. And there's a bigger left tail than the right tail. And when you have that, that is a skewed left graph. On the other hand, if we draw something like this here, where you go further out to the right compared to the left from the center of the high point graph here, that's a skewed right graph. And these also do happen sometimes. For example, if I wanted to look at, say, income, or if I wanted to look at housing prices, these are two examples where they would be skewed right in that you know, most people are going to have an income in a certain region here, but then there, you know, are some people that are earning less than them, but there isn't that much less you could possibly earn, right? I mean, it's not like that common salary is super high. On the other hand, there are going to be people that are making 2, 3, 10, 20 times what that average salary is. I mean, throw in the CEOs there, they're going to be data points really far on the right here. So that would be a skewed right graph. Similarly for housing prices, you know, most houses are in a certain range in a given area at least, but then there are going to be houses that are significantly more expensive, right? If you look at Southern California, you're going to have a very skewed right graph here because there are those houses, say in Malibu, that are just insanely expensive. Those are going to be data points way out here on your graph, you know, like 10 million, 20 million, 30 million, whereas most homes are maybe in the 500,000 range in Orange County. So you can have skewed right graphs, you can have skewed left graphs. To be honest, I've never really had a lot of good examples for naturally skewed left graphs, and I'd be happy if anyone comes up with one and share it with me. But there is one that I saw before, I kind of like it, but it's not great. Is let's suppose you broke open a vending machine that had a bunch of coins in it, and you looked at the year that the coin was minted. Well, most of the coins are going to be from recent years, but then there might be some coins from older years and older years and older years, so on. Maybe even have like a 30, 40, 50-year-old coin in there. Maybe someone had it just lying around and ended up using it in the vending machine. And so that could be something that would turn out to be skewed left. So like I said, I don't have a lot of great examples for that one, but they do happen. And you want to know this terminology here because we're going to use examples that follow these. And then we're also going to have certain rules that we can use when it's, for example, a bell-shaped graph that would not work if it was skewed left. So understanding these words and the pictures and how they function is going to be important for other calculations we're going to do later on.